All right, Aaron, what's x plus 1 to the 0?
1.
Awesome. Faith, what's x plus 1 to the first? Kyle, x plus 1 squared. Plus what? 1 times 1 is 1, right? X plus 1, the quantity cubed. Rachel.
X cubed plus 3x squared plus 3x plus 1.
Excellent. And let's see, Nick Bailey, x plus 1, the quantity to the fourth. All right. Do these numbers look familiar?
Nope. No. Yeah.
No?
No,
Oh, it's that triangle thing.
Yes.
Oh,
The triangle thing.
yeah.
You mean this?
Yes.
Oh, I remember that.
All right. This is called Pascal's triangle. Okay? Notice how if you take any two numbers, it adds to the number in the next row in between them.
What?
Okay? What would our next row be? We would always have a 1, then a 6, then. Beautiful. Pascal's triangle describes the coefficients of a binomial to a power. What? They don't add up to, like, if I take the 2, like 10 comes from 4 plus 6. What? Okay. Now, where do these numbers come from? Okay, there's a relationship with these numbers to something else. It's not quite what I'm looking for. Combinations. Does it relate to combinations at all? You don't know how? Okay. Well, since like this we count as row 0. This we count as row 3. This is combination 3, choose 0. Combination 3, choose 1. Combination 3, choose 2. Combination 3, choose 3. Okay, yeah, ringing a bell? Okay, so instead of remembering every single row of Pascal's triangle, this is how we get the expansion of a binomial to a power. Write it down. Okay, so this big sigma means what? Add them all together, okay? when we expand a binomial, we're going to get the sum of some terms, right?
Right.
So, we plug in 0 to get our first term, we plug in 1 to get our next term, 2, yada yada, until we get to n choose n. Okay? And you can say this is n combinations of r, or n choose r is sometimes how we'll say it. Okay, but it's called a combination, and this is what we call, well, it's a part of our binomial coefficient. Now, if there's a coefficient with 2 and y, then our coefficient's a little bit more than just the combination. Okay? Now, just like I said before, Pascal's triangle here is a triangle of combinations, where in our 0 row we have 0 combinations of 0. In our 3rd row, this is what I pointed out before, okay? We start out with 3 combinations of 0, and we keep adding 1 until we get to 3 combinations of 3. Okay? You remember this from last year, correct? What? That's what we'll talk about today, right?
Right.
So, like, if I have something to the 4th power, I will have 5 terms, where these are our coefficients. How many ways can you take 3 items and choose 3 of them? 3. Because in combinations, order doesn't matter. Okay? All right. So, this is how we find a combination. You have a nice little way in your calculator, don't you?
Yeah. Sure. Really?
Yeah, write the formula down. And we'll talk about it more on Monday as well. We talk about permutations and combinations. Oh, that's just fun stuff here, guys.
Oh, I remember this.
Now, when you put it in your calculator, if you went like 5, choose 2, you need to press 5, then the combination, then 2. And then hit enter. Okay? Some of these you should not need to plug in your calculator. Like 3, choose 0. You should know that's 1. Okay? Here is another way that combinations could be written. Okay? So this is the n combinations of r, n choose r. Okay? Please know, please understand that you have 2 different notations for it. Not that I can think of. No. Okay? So 8 combinations of 2. If we use the formula, then it would be 8 factorial over 2 factorial times 8 minus 2 is 6 factorial. Okay, let's just recall how to reduce fractions with factorials. Yes.
Take out the 6 factorial and the first 6.
So 8 times 7 times 6 factorial, right, is what I can say this is. 6 factorial, 2 factorial, 2 times 1. So those cancel, and we have 8 times 7 divided by 2, which is 28. Put it in your calculator for that practice. Punch in 8. Find your combination button, and then 2. Yes.
Okay.
Is your answer 8?
I know, she did. Okay, put this one in your calculator. All right, what is 10 combinations of 3?
120.
120, awesome. So now let's actually do some expanding here. Two x minus 3, the quantity to the fourth. Okay, so our n is 4. We will always start out with n choose 0. Okay, so 4 combinations of 0 times, we need 2x to a power, and we need negative 3 to a power. Good. Whatever you have right here for your r, 4 combinations of r, that is going to match the coefficient of y. Okay, your second term in the Bible. Okay, so then we have 4 combinations of 0. Now we're going to go to 4 combinations of 1, where this is going to decrease by 1 power, and negative 3 is going to increase by 1 power. Okay? Then we have 4 combinations of 2. 2x decreases by a power, negative 3 increases by a power. Plus 4 combinations of 3. Now we have 2x to the first and negative 3 to the third. Notice how whatever we have for r matches the coefficient of our second term of the binomial. And then plus 4 combinations of 0, 2x to the 0, negative 3 to the fourth. Yes, thank you. I'm sorry. 4 combinations of 4. Okay. I was getting ahead of myself. I was thinking that 2x negative 0 exponent. Okay, now, 4 combinations of 0. We don't need our calculator. What is it? 1. 2x to the fourth. And negative 3 to the 0. Plus, you don't need a calculator. 4 combinations of what? How many ways can we take 4 items and choose 1? 4. 2x cubed. 8x cubed times 3. Plus 4 combinations of 2. 6. Times 2x squared times negative 3 squared. Positive 9. 4 combinations of 3. 4. Okay, there's always going to be symmetry with your combinations. 1, 4, 6, 4, 1 is how this line could go. So 4 times 2x to the first times negative negative 3 cubed. Okay? And then 4 combinations of 4 is 2x to the 0 and negative 3 to the 4th. Okay? So we have 16x to the 4th minus 96x cubed plus 216x squared minus, that's how much? 216x plus 81. Now, this may have seemed slightly tedious, but is it better than multiplying two binomials together and then multiplying that trinomial to a binomial and then multiplying that 4-term polynomial to a binomial? Okay, now if we're raised, the higher the power, the more efficient this is. This also alleviates some of your multiplication errors. If you're multiplying polynomials together 3 or 4 times, there's a pretty good chance you're gonna, I mean, not a pretty good chance, but you could have some multiplication errors or combining like term errors. Okay? Okay? You can also go from this first step all the way down to here. Technically, you don't need this middle step unless it's going to help you. Okay? Alright, let's do x squared plus 4, the quantity cubed. Okay, so now our first term is just x squared. Our second term is a positive 4. Okay, so 3 is our n, so we start with 3 combinations of 0. X squared is our first term, it gets raised to the, and positive 4 gets raised to the 0. 3 combinations of 1, x squared is being raised to the 4 to the 3 combinations of 2, x squared is raised to the, and 4 to the, and then finally 3 combinations of 3, x squared to the 0, and 4 is being cubed. Okay? So let's do this. 3 combinations of 0 times 4 to the 0, and x squared cubed. 3 combinations of 1 times 4 to the first. So 3 times 4, x squared squared. 3 combinations of 2, 4 squared. 16 times 3. What? So 48. Here are 2 different things. And then x squared to the first. 3 combinations of 3, x squared to the 0, or cube. 64. It's because x squared is our term, okay? So since it's x squared, we're going to go down by 2 each time. If this was x cubed, we go down by 3 with our powers each time. Does that make sense? Yeah? Okay. Is everyone okay with these 2 examples? Okay? Now, sometimes I'll ask you to do an entire expansion. Sometimes I will ask you for a certain term or a certain coefficient. So, I want the sixth term of a plus 2b, the quantity to the eighth. Now, if we expanded this out, this would be twice, right? Okay. Now, let's think about this. Our first term is going to start with 8 combination 0. So if I want the sixth term, we want 8 combination 5. Everyone okay with that logic?
Yes.
Okay. We're going to have a to a power, and we're going to have 2b to a power. Which one matches this 5? The second one. So 2b is to the 5th, which means a has to be to the what? Third, because our, I guess I kind of forgot to point this out. Between the two terms, the exponent should add to this number right here.
Wait, I thought the y was
The y is whatever this is right here.
Oh, the
Notice 1, 2, 2, 3, 3. Okay. So is everyone okay here? All right. So what is 8 combinations of 5? Times a cubed times 2b to the 5th is what? 32b to the 5th, which means we have y is what? That 2 needs the power 2.
No, yeah.
Okay, what's 56 times 32?
That would be 752.
There's our sixth term. 8 combinations of 5, just put it in your calculator. Yeah. Do not memorize. I mean, you can know the Pascal's triangle for like 1, 3, 3, 1, 1, 4, 6, 4, 1. But don't write it out to get the 10th row. Okay, you can use your calculator for the combinations. Let's be efficient with our time. Okay. But using the Pascal's triangle for cubed, fourth, even to the 5th, you know, that's not a big deal. All right. Now, I want the coefficient of a to the 6th, b to the 5th. Okay. Is it as simple as just the combination? No, because I have 3a and negative 2b. That 3 and negative 2, those are going to affect the coefficient. So, first of all, let's go ahead and just set up. We're going to have 11 combinations of something. We're going to have 3a being raised to a power and negative 2b being raised to the power. What is 3a going to be raised to? The 6. What is negative 2b being raised to? The 5th. Which means right here we have 11 combinations of
5.
Okay. So for our coefficient, what is 11 combinations of 5? Use your calculator.
Okay.
462 times, I don't care about the a, I only care about the coefficient. So what's 3 to the 6? Negative 2 to the 5th. Okay? And when we multiply those numbers together,
It's pretty cool.
10,775,536.
and it's negative. Well, it's asking for the coefficient. So all I want is the number that would be in front of a to the 6th, b to the 5th. Okay? Any questions? Is this coming back? It's not that bad, is it? No. There you go.